What if you don't like my presentation? Then you don't. Anyway, thank you very much for coming for the presentation. Obviously, this is going to be in English. I don't speak Italian. I'll try to speak slowly. You know, my wife tells me all the time, talk slowly, talk slowly. You speak so fast. And I don't know if you have ever interacted with Indians. Indians speak language very, very fast. And I don't know what the reason is. Maybe they're going to miss the train, they're going to catch it. I don't know what it is. But we speak very fast. I'll try to talk so slowly. I'm going to talk about 3D point clouds, especially the deep learning part of it. It's going to be around 45 minutes of presentation. You can always ask questions anytime you want. Image processing has become so popular in the recent past. 2012 was the first time CNNs were introduced. And by the time it was 2015, the models were so popular that the performance of CNNs surpassed human performance. So if you look into this, in 2015, the average top 5 error rate of a CNN-based model is 3.6%. That means if you show 100 images to a model based on CNN, it only makes mistakes in 4 images. Do you know what the human performance is? 6%. So in 2015, models have already surpassed the human performance. In 2016, that number went down to 3, and 2017, the number went down to 2.6%. So in other words, even though the percentage rates are increasing slowly, the accuracy rates, models are reaching very close to 100%. Various 3D LiDARs or sensors are becoming cheaper and cheaper. 4 years ago, if a LiDAR is set up on an autonomous car, it used to cost $20,000 to $30,000. Now I think it's come down to $5,000, and I'm sure in the next couple of years, it will be cheap enough to go on your smartphone or your mobile phone. So, because the real world is in 3D, it's not in 2D. So there will be more need for having 3D image processing, not just 2D image processing. So research has really improved in the last 2 years. 2017 and 2018 is when a lot more papers are published by research organizations on how to process 3D point clouds. My company actually creates LiDARs, which if you keep in this room, it only is of this size and it weighs 2 pounds. It goes on the backpack if you want to. If you put it in this room, and this is of course a very simple room, just a few doors and walls and ceilings and floors, but if you put it in a factory where there are so many pipes and engines and pumps and walls, for such a fine defined place, it takes 2 minutes to take a 360 degrees image. The size of the point cloud is almost half a terabyte. And we are having problems on even as simple as how do I carry a half a terabyte image, because in a factory, let's say there's only one floor factory, and typically factories could be of the size 100 meters by 100 meters size, and you need to have at least 10 different locations where you take the picture or point clouds images. So you're talking about 5 to 10 terabytes of images coming in. Where do you store it? And especially if factories are outside the cities and you don't have the cloud connectivity as much. Many times we are supposed to work offline. So whether it's healthcare industry, where you have CT scans, which is a 3D image, in autonomous cars, when I say autonomous cars, not just cars, but could be drones and anything which is flying and moving, or even robots, and any type of maybe satellite images or images you take using 3D images, there is a need for deep learning methods to process that and identify what's in the image. For example, in 2D imaging, which happened in 2012 and later, the earliest solutions were in terms of classification. Let's say if you take a picture of a cat or a dog, the model has to find out whether it's a cat or dog, so it's a classification. Then came the localization and detection. Let's say if you have multiple cats or multiple dogs in a picture, the model has to identify how many cats are there and how many dogs are there. And later on came the semantic segmentation. If you want to really find the boundaries of various objects, which is used for any in healthcare industry too. The same applies for 3D processing too. Models are being designed as of today to do classification, and the next step would be identity localization and detection, and also semantic segmentation. I'm going to talk about around 10 different papers. Some papers I'll explain a little more, and some papers I'll explain a little less. Some are really pioneering papers. I'll explain those. Obviously, in 45 minutes, I'll not be able to talk every detail about point clouds. Every time I show a paper, I do have the link at the bottom of the slide, and you can check for additional information. Before I start even talking about the point cloud solutions available, the representations of 3D data, there are descriptors, projections, and RGBD, RGB, and depth. Descriptors and projections is a type of data where a 3D image is projected onto a 2D space, and then you run a CNN model to understand what's happening. But these models are not very effective. These were published in 2016 and even maybe some in 2015. They're not very effective. RGBD is so-called 2.5 dimension images, because you have the RGB in 2 dimensions, and then depth is a 3rd dimension or a half dimension. And there are models which actually can process RGB data, but that's also not very effective. But if you're looking for a low accuracy and low compute models, they are available running on RGBD. Volumetric data is that data which, if you have, let's say this is an image, let's say this is a cup, and there is an empty volume inside, but you see the surface outside. And if you take a 3D point cloud, points are all on the surface. There are no points inside. But to have a regular data out of this irregular data, you make it as a volume. So you think the entire volume is filled with information, and then use only the surface of it. That's called volumetric data, which is voxelization, voxels. Voxel is nothing but you create a 3D volumetric data object of a hollow object. There are octrees and voxels which are made out of 3D volumetric data. I'll show a couple of models which actually use the octree structure, and I'll talk about how it's not that effective. Multi-view is another 3D representation. For example, if you want a 3D image of this chair, you can take a 2D image of this chair from multiple views around it. It could be 8 views or even 10 views or 12 views. And then you can write a software that can stitch all of those images together. So you can take 2D images of the chair, run a CNN model, and understand what perspective you're looking from. For example, if you take a picture from this side, if you take a picture from this side, and if you take a picture from this side, sometimes you see the legs, sometimes you don't see the legs. Sometimes you just see only the back support, once you see the bottom support. All of this information the model processes and then gets a complete understanding of it, and you can stitch the 2D images out of that. That was easy because you can translate the CNN-based 2D models to 3D images too, but that's not very effective. It's actually computing, it's expensive. All of these can be Euclidean, you can call as Euclidean data space, because if there is a regular data set where you have a distance metric from any point to the other point easily measured, that's called Euclidean data space. All of the images I talked about comply with that Euclidean data space expectations. In the non-Euclidean, you get point clouds, graphs, and meshes, but I do have to clarify that there is a debate going on among AI scientists whether point clouds is part of Euclidean or non-Euclidean. You know, the problem with AI scientists, they don't agree with each other, and that's what is happening. So I have put it here as a non-Euclidean data structure, but there actually many solutions available today assume that point clouds are Euclidean data space and run multiple image processing models. Meshes are a type of data structure where you would imagine the 3D image is a collection of polygons. Many times it could be triangles. And all of these triangles are connected with each other on the vertices. And now you convert an irregular data structure of a point cloud to kind of regular data structure, because now you know where the vertices are, and from one vertex of a triangle you go to the other vertex and you go to the other vertex of the triangle, and you can traverse and you can measure what's happening. But meshes are also not very effective in terms of data translation. One best thing about point clouds is point clouds are invariant to rotation. For example, if you take an image of this room, a point cloud image of this, if you rotate it, it's still the same room, it's the same information relative. This wall and that wall on those pillars are all in the same position, they're just rotating. With respect to each, they remain the same, they're invariant to rotation. Also, 3D point clouds are canonical. When I say canonical, you can convert a 2D image into a point cloud, 3D point cloud, and also you can do the reverse too. That's the advantage of point clouds. These are some of the models available. This is a quick snapshot of how an image processing model can work on different types of data. I will talk, of course, more on about the point clouds, but if you watch carefully these solutions, the initial objective by many experts was, how can I use a 2D CNN onto a 3D image and process it? And the reason being, CNNs as neural networks to process images were well established. There was a lot of knowledge available, and hence there was extension of doing it. One of the first models I want to talk about, this is all published after 2017 and 2018. And you can see the link at the bottom of each slide. This is all papers published. You see the numbering system is 1712, means the December 7th, 2017 was when the paper was published. So it's very, very recent, not more than 12 months ago. In this paper, you take an object, could be, for example, let's say an airplane, but let's say you take an object and you start recursively breaking down the picture into 8 pieces. So you have the main node and you have sub-nodes of 8, and each sub-node will have 8 more sub-nodes and keep on breaking it down till you reach certain manageable level, and each node will have a volume space like a typical 2D image. So if you end up breaking down this into 8 pieces and this 8 pieces into 64 pieces and go on till you reach a certain level, you actually have stacked images of each of this small cube. And typically it could be 1 or 2 point clouds, and each point cloud will have the XYZ dimensions on it. And you can, once you convert this image using OCtNet data structure into a volume space like this, which is stacked on top of each other, and then regular CNN processing. Are you familiar with the CNN 2D imaging, where you have a kernel which actually convolves on top of images and then makes sense out of it? Are you? Yeah? In India, for yes we say yes, no we do this. And if you don't say anything, I would not know what you're saying. But I will make an assumption that you're familiar with that. So if you think about how a 2D image processing is done, in this paper, all that they're doing is, how do I convert a 3D image into a 2D image using OCtNet data structures? And this paper, I think, reached really good accuracies. There's another paper which actually has exactly the same logic. They also use, it's called OCtNet, and they used a similar logic, and it's published, I think, a couple of end of 2016. Both of them were initial pioneering papers which were published. I won't explain, but this is the architecture of the model. You see a bunch of convolutional layers, and then you also have the pooling and unpooling. So you have the pooling, which actually brings the the space of the image brings it down to smaller, and then you do unpooling, which will increase it and then increase the image space. PointNet is the most popular of all the models available today. This is published in 2017. There is an upgraded version of PointNet called PointNet++. PointNet is the first time a model used for point clouds processing where the model takes point clouds as a raw format. No pre-processing is required if you want to process a point clouds for semantic segmentation or object classification. So let me explain in detail. Here, the authors say that because point clouds are invariant to rotation, you take any point and you have the XYZ coordinates of the point, or if you want to add additional coordinates like XYZ and maybe intensity, color variation, whatever is the details you want to add, that becomes the vector of every point. And if you arrange the points in a matrix, in just a table one after the other, and if you sort those points up or down, the processing result will not change. In other words, they found a symmetric function to process on a point cloud. What's a symmetric function? A function when you apply irrespective of the sequence and still get the same result, that's called a symmetric function. For example, addition is a symmetric function. 2 plus 3 is same as 3 plus 2. Similarly, multiplication is a symmetric function. Max pooling is a symmetric function. In whatever way you apply max pooling, you still get the same result. So they apply a symmetric function. In this case, the major symmetric function is the max pooling. So they take the raw data, so you have n number of points, each of them have XYZ coordinates, you have so many points, and you just do a initial input transformation, and then you also do a feature transformation. And what it means is nothing else but like the skip connections you use in ResNets, where you do 1 by 1 and 3 by 3 convolutions, and then reduce the dimensions, and then expand the dimensions, and you just do that and do the transformation, and after that you use a regular multi-layer perceptron, which is like a typical RNN. So you take all the raw points, you can transform because it's the invariant rotation. You can arrange them in any order and then run a multi-layer perceptron. And after you do multiple types of that activations, you do a max pooling to get the global feature. So in other words, let's say you take an image of this. At a global level, you want to find out whether it's a room or not. You would ignore the tables and chairs and maybe the walls, but at the global level, this is a room, and the model actually figures out, as part of this global feature, it understands what is the image about. So obviously, when you run this model, you cannot take entire room like this, but you just take individual images like a mug or a table or a car or a chair, and it will look at the entire image. In this case, for example, for the chair, this is the base where you sit. These are the 4 different legs. But at a global level, it's chair, and it just picks up. So in this network, which is more of a classification network, there are 2 different networks. The classification network will do a global feature of what the image is about, and then you get a scores. You typically, for example, you have a classification scores. But if you want to do a semantic segmentation on top of it, you use the same global feature and add it to the local features you are getting. So when I say local features, you have this table, you have this chair, and you also have these legs. For semantic segmentation, you need to understand this is a class called chair, but also understand where the parts of the body is. You need to actually identify the border or the edges of all the 4 legs and the base. And that is done by using the global features concatenated to each point that is coming in. So in other words, what's happening in summary is, for every point, you process every point, identify one single global feature for the image, and concatenate the global feature to every point in the point cloud. And then run it again using multiple layers of multiple perceptrons. So in this network, there are two networks here. In using this network, you can do a classification, and using this network, you can do a segmentation, semantic segmentation. So if you give an image, complex image like this, you can start identifying the walls and the ceiling, and also of course the chairs and the tables, and you can see different chairs are semantically identified. So it's called instance segmentation. You have different instances of chairs are accurately segmented. Now the best part of this paper is when it was published in 2017, many of the solutions available till then, for example, projecting a 3D image into a 2D and running an image processing, or using multi-view images of the same point cloud and then doing a CNN on top, this model beat all other models very, very easily. So that was, from that sense, PointNet is a pioneering paper, and I think they have open sourced the code, and also I think you find some pre-trained models available for PointNet. These are some of the models. Here's the multi-view CNN model that was published, I think in 2015 or something, and this model actually beat that very, very high. The average accuracy is lower, but you can see the overall accuracy is actually almost same. And there are a couple of good points in PointNet. One is when they dropped the density of a point cloud by 50%, the accuracy rates dropped only by 2%. Now, why would you drop the number of points? Because when you have a LiDAR on your autonomous car and the car is moving fast, or the objects around it, like there are other cars, they are moving too, the LiDAR will not have enough time to capture every detail very, very clearly. So the density varies all the time. And also if the vision is blurry, for example, if it's raining or if it's dust, the point cloud will not be very, very accurate. And at that time, you have huge noise coming in too, and the number of points could be varying. This model, the accuracy rate dropped only by 2% or even lesser, even if you drop 50% of the point. That was actually the best part of it. And it actually converges very, very fast too. So that's about PointNet. And there was another network that was published almost at the same time, which is using the same logic as the octrees. Here, they picked a k-dimensional tree structure for the point cloud. And in this case, k I think is 8 in this case, in this model they picked up, but it could be any other dimension too. KD tree network is you break down the point cloud into a tree structure of k dimensions and then run a CNN type of model. This did not pick up as much popularity, but if you look into look at this, PointNet this model actually beat the PointNet also very, very easily, all published at the same time. This was not very attractive, but then immediately the authors came out with an upgraded version of PointNet model called PointNet++. Now what's the fundamental difference here? If you take a complex image like this room with multiple chairs and people and then walls and ceiling, the PointNet model, the initial model, was not converging fast enough at the local level. So a small chair or the legs of the chair, it was not being actively captured by the model, even though it captures maybe a big picture like a chair or like a big massive table, or can identify a big image like a room. It was not focusing on the local features. So what they did was they actually picked a few points, any few points. Let's say they just picked only one leg of a chair and run a PointNet on it. And remember, I said you create a global feature, but because you are running a PointNet on just the leg of it, the leg, even though it's a global feature, but it's actually a local feature in the context of the overall image. So you recursively run PointNets multiple times on different aspects of your point cloud. So the model is running multiple times, it gathers the local features, and then eventually becomes really intelligent when it comes to semantic segmentation. The accuracy rates went up a lot, and the images, especially a complex image like in a factory environment, we have multiple pipes and tubes, and it was accurately identifying the semantic segmentation of those pieces. But the computing cost went up because you're running PointNet so many times on the same image. So if you're looking to develop an image processing model for 3D point clouds, PointNet would be a really good starting point. PointNet++, even though it's very higher accuracy, the computing cost is very high, especially if you're trying to, if you use the model on the cloud, I think it's fine, but if you want to use the model on your, let's say, a mobile device, or let's say even on your autonomous car, it becomes a little more complicated. There are a bunch of other models, but this was a very interesting concept. SLATNet, Sparse Lattice Network, they made it short, and they introduced a new concept called bilateral convolutional layer. I'll explain that. Look at this image here. So you have these random dots, because when you have the point cloud, they'll be appearing anywhere in the space, 3D space. And the fundamental reason why you could not apply the regular CNN approach is these are irregular format. The author said, can we translate this irregular data into a regular format? So they created a triangular mesh like this, and obviously like a point falls within a triangle, sometimes very close to a vertex or very close to another vertex, on the vertex or somewhere at the bottom or on the line or the edge. But every point they would allocate the intensity of each point to each of the vertex within a triangle. For example, you see this point which is in the middle, they would allocate the point to the 3 different vertices which it's enclosed. And if there is 2 other points here, they would be allocating these points to this vertex too, which is concatenated or added to whatever intensity you're getting. So in other words, you are converting this irregular data into some regular format. And after that, they create a convolutional kernel which is of the same shape. Typically, you might have heard a CNN-based kernel could be a 2x2 or a 3x3, which is more of a square shape. I mean, it could be sometimes rectangular shape, but predominantly square shape. But here, this is a lattice shape. And after that, they just do the regular they convolve. The kernel, which is this lattice space, will convolve on this image and start making sense. And after the whole processing done, they actually undo it and allocate to the right position. The accuracy rates of these models also was very, very high. But then I think I haven't heard of this model being used too many times. They used both for 2D images and 3D images, and if you have 2D images, this model works too. There is not much of a fundamental difference in this model. The only concept they have added here is an encoder and decoder. I remember the concept of encoder and decoder was used first, I think, in NLP, natural language processing, around 6-7 years ago, where if you're doing a language translation from, let's say, English to Italian or Italian to English, you have an encoder which actually reads a sentence in a source language and then converts that into a target language. And that's when the concept of encoder and decoder came in. Then it's called sequence-to-sequence model, because you have a sequence coming in and a sequence going out, and the sequence that's coming in is used by an encoder, and the sequence that's going out is used by a decoder. But the first time they used an encoder-decoder for processing 3D point cloud, otherwise the concept remains the same. The architecture is published there, but and they do have, I think they do have published, the results are better than some of the models previously published. I don't think they are open source this code, but again, this is published as recent as July of this year. There are a couple of other models that comes after this, where SqueezeSeg is a 3D point cloud processing model, which was based on SqueezeNet. There's a 2D image processing model that was proposed some time ago. The authors used the same concept to develop a 3D processing model, and they called it a SqueezeSeg, where they do convolutions and deconvolutions, where using convolutions you can bring down the space, the feature space of an image, and then do a deconvolve to increase the feature space. And they also do these skip connections where the feature space that the model learned here, even though that is passed through these different layers, and by the time it reaches here, it gets the inputs not just from this layer, but also gets input directly from this layer. And then you can see a similar connections between all the corresponding layers. This actually made the model remember the processing that happened just one layer before, but also 4 layers or 5 layers before. That actually made the remembrance power of the model up. And this also actually achieved quite a good performance. And another interesting feature is they actually used conditional random field as an RNN layer for the processing. Other than this, there's not much of a change from a regular SqueezeNet model where they're used for 2D processing. Similar model again is PointNet, not the regular PointNet for 3D processing. There was another model called PointNet. So PointSeg is another model published again in July of this year. They do the convolutions and deconvolutions, but on a data set for an outdoor data set for cars and pedestrians and cyclists, the model actually do a fantastic job. So you have that downsampling, which is typically used like in a ResNet. You do convolution of 1x1 convolutions, the size drops by 1/4, and do one more 1x1 and one more 3x3. You do half and half, and you do concatenate. You bring the original dimension of the data set back before you pass it on to the next layers. They do have, I think, source code available, just in case if you want to run it yourself. We, as a company, we are also working on developing various point cloud processing models. Sometimes we do look at the code availability too. There are a lot of other models available. I will not talk about it. If you want, I'll give you the slides. You can go check these papers. All of these papers are really, really worthwhile papers for processing point clouds. There's another model available. Here is an interesting concept. In processing 2D images, you have the kernel the shape of a square or a rectangle. Now later on, when papers were published on 3D dataset processing, the shape of the kernel also became a cube shape. So instead of doing 3x3, you have 3x3x3. So that's a kernel which is convolving on the 3D image. Here, for the first time, the authors proposed, can the kernel, the convolutional kernel, also be the shape of a sphere, not like a cube? And that was a really interesting idea they proposed, and they came out. And the model actually performed well too. If you look into some of the accuracy rates, it is better than some of the previous models, but again, not dramatically higher, maybe a couple of percentage points. But the differentiating factor in this case is the kernel for convolutions was a spherical shape. That's why it's interesting for me. I never tested it myself, but it's a very interesting concept they're using. I'll skip this. If you're looking for data sets to process, and I'm sure you know in AI, the biggest stumbling block for any company or for any research is lack of data sets, availability of data sets. In 2D images like CFAR and ImageNet, etc., there's a lot of data sets available in the last 4 or 5 years. But 3D point clouds, there's a lot of research and a lot of collaboration going on to create more and more data sets. These are some of the data sets available. The most popular are these two, ShapeNet and ModelNet. ModelNet actually has 2 different types of data set. One is a 10 class data set, and you also have a 40 class data sets. And these people use these data sets for computing. Now, if you go to the website, you have a leaderboard of how various models are performing and what the accuracy rates are. And you see some of these data sets I kind of like. For example, Flying Things 3D is a synthetic data set. Normally, when we do 3D processing point cloud model, we would want to use a real data set, not synthetic data set. But there are situations where if you are into manufacturing of components and you're designing, and if you're designing synthetic components and if you want a model to identify any defects in the synthetic model, you can train a model on a synthetic data set, and this could be an interesting scenario there. and there are some old data sets which are not being upgraded, but most commonly used are ModernNet and ShapeNet. I know some people use Pascal Walk and also Kitty. Kitty is another popularly used 3D point clouds. But there's a lot of data set available, thankfully, even though the research has picked up only in the last 2 or 3 years in point clouds. This paper for the first time talks about 3D processing of images and at the same time 2D processing of images, and it combines together to actually make sense in terms of accuracies. The architecture wise, you can see there are a bunch of convolutions and poolings happening, but this the differentiating factor is they do a multi-view, which is a 2D image processing, and also add the 3D point cloud into together, concatenate that, and then process the images. And the model actually does a really good job in terms of overall accuracy. I have 2 other papers I really want to highlight, even though I will not explain. In 2015 and even 14, when 2D processing was really picking up, there's a lot more focus on how do I process videos that's coming in, especially in smart city solutions. We have a surveillance camera in a city like Turino. You want the surveillance camera to find out what's happening, and if there is a crime happening, only then react. Otherwise, you don't need to do anything. So 2D processing of video became really popular. But right now, I think only in the last 6 months, there's a lot more research on how do I process a 3D point cloud image, especially video of things moving. How do I find out the flow of action? And these are a couple of papers. FlowNet is one paper, and YOLO 3D. I'm sure you've heard of YOLO 2D. YOLO was published, I think, in 4 or 5 years ago. YOLO 1 was, YOLO stands for You Only Live Once. Not the one you thought about. It's You Only Live Once. And that, initially YOLO version 1 was only around 45 frames per second. It was not really usable for autonomous cars. The next one, I think, came with 224 frames per second, really improved in the accuracies. YOLO 3 was a little less accuracy, but it works really well on mobile devices and really computes fast with less computing time. So YOLO was used again in the concept of using point clouds, and they came out of the model. I don't have the link here, but if you go to the website, I think YOLO 3D, you'll find information about it too. But the architecture is very similar, but very simple to understand too. A bunch of convolutions that happens on these images and then identifies. It's not giving the same accuracies as some of the other models, but this is a good starting point. I'm sure maybe in the next 6 months or even 12 months, YOLO will come out with a better version of processing point clouds, especially the action flow of the video. PointFlowNet is another model which is quite popular. You can see it sounds very complex, but when you really start looking at the architecture, it's quite simple. But I won't go into the details about the reason I picked up these 3 is that there's a research that just started on how do I make sense of a video of point clouds. If you actually have a LiDAR which is traveling with an autonomous car, can I make sense of all the cars and the pedestrians and the trees and the road fast enough and still be very accurate? And that's what is the attention being paid. Now, these are all published papers, but I'm sure companies like Baidu, Google, and Tesla, and some of the other companies that are working on autonomous cars, they have not published their research on how they're doing. They're using LiDARs for detection. I'm sure they do have good solutions available, but we don't know yet what they're using. Now, let's say if you want to play with some point cloud, and like TensorFlow for 2D images or NLP or machine learning, there are a couple of frameworks available you can play with. Point cloud library is one framework where you have a bunch of modules available. How you can process the data or pre-process the data or do some model generation. This is a good set of information if you want to play with. And there's another framework called Cilantro. This is not as famous, but it has also lots of modules available. It also comes with a bunch of other features that you can run on your point clouds. So if you have the point cloud data set, so there are open source data sets available, and there are libraries available you can use to play around to develop your point cloud solutions. Or if you want to start using any of the existing point cloud pre-trained models, I think you should be able to download it and start playing around with that.
Thank you. In the end, they enjoyed it.
Yeah. Thank you. You're really polite guys. Yeah, thank you. If you have any questions, I'll be happy to answer.
Yeah. At Hexagon, do you use this kind of technology?
We have LiDARs right now which we take images for. Let's say if you have a factory, let's say your factory is done 20 years ago. Normally a factory costs around $500 million to $1 billion. It will run for 50 years to 100 years. So let's say 20 years ago you developed your factory and you have used some software models to construct the factory, but now that software, 3D modeling software, is not available anymore, and even the designs, the layout designs, are just only papers. You don't have any more soft copies of it. But using the latest technology, if you want to create the digital twin of your factory, what many companies are doing is they are doing an OCR of this PNID. It's called process and instrumentation diagrams, and then taking the pictures, 3D pictures of the factory, and converting them into using models, identifying what is what, and connecting the paper layout diagrams with the reality in the factory. And then you can maintain them as digital twins. In that process, we have created, we do have LiDARs. For example, the most recent LiDAR we released is called BLK360. That's the one which I said, it only weighs 2 pounds, and it can take a complex, high-definition picture of the size of 1 terabyte in less than 2 minutes, and then you can take such multiple pictures. And we do have 3D modeling solutions available, and you can use these 3D modeling solutions on this point clouds, and you can do some other modifications and stuff. The best benefit of this approach is if you have a digital twin, and let's say after some time you want to replace a turbine which is kept there on the second floor of the factory, but all other structures remains the same. You cannot just take out the turbine and put a new turbine there, because then the changes in the pipes and the wiring, and maybe sometimes the walls or the supporting structure has to be changed. You cannot do changes in a live factory, and you want to do it on the software solution design side to see if this even fits or not. If I have a point cloud processing model, and if I do a real semantic segmentation, I can identify where the turbine is, and I can just take all the pixels out. Now I have an empty space there, and I fill the empty space with, let's just say, only the floor. Now it looks like the image is exactly the same image, but without the turbine. Now, if I know I'm going to put a new turbine there, I'm going to get the point cloud image of that turbine alone and drag and drop it there to see if it fits or not. So that type of designing in the office room, and not really the factory floor, can be done if you do a digital twin and if you actually have a point cloud processing model. So we have the LiDAR which actually takes point clouds. We also have 3D modeling solutions. We also now going to be having point cloud processing models which will help you, designers or architects of factories, to how to make changes to the factories.
In terms of development, I've seen many of the architectures that you have presented have special use either convolutional layers that are really specific to the nature of 3D point clouds. What would you say is the best framework for deep learning to apply to these kind of models?
Right now the research is still in infancy for the point cloud processing today, because the amount of annotated data is not much. It's very expensive for example, for a 0.5 terabyte size of a data, let's say even as simple as this room, it may take 6 to 7 hours for just the pure annotations, and hence it's very expensive. So the data sets available are some limited number of data sets available to play around. And hence, many times, it's a natural tendency for researchers to use the 2D solutions or image processing solutions that are applied for 2D and use the same thing for 3D too. So right now, the square or rectangular shaped kernels are being used for processing. There are a couple of experiments on 3D shaped kernels or the spherical shaped kernels, which I showed you too. The sparse lattice networks, the lattice shaped kernels are being used too. There is no one single method which is really overwhelmingly being accepted, because the research is just happening today for the last, let's say, year and a half. So I don't know eventually which one they're going to focus on, but right now the PointNet and PointNet++ model is really appealing to the people, because it is you can input the raw point cloud data without making any changes, and also because of the max pooling feature, the computing cost is really short, because you're actually eliminating a few of the computation activities and doing a max pooling. Other than that, I don't have an answer for your question. I think we'll have to wait and watch how the research emerges.
Having a 3D cloud point of cloud, what's the best way to determine the surfaces of the objects? So if I have the point cloud of this chair, what's the algorithm that's best to determine the mesh?
I think what you're talking about is, I think, semantically segment. Let's say if you have these two chairs in one image, and if you want to find out where does this chair end and where does this chair start, if you want to really find the boundaries of it, which is nothing else but semantic segmentation, all of the models actually can do a good job of semantic segmentation. Point clouds, as I meant, PointNet, the first one, actually can do a decent job, but because of the local features, it is not really good. Sometimes, if you see these two chairs, the legs of these two chairs are so close to each other, maybe the model may get confused. It will think it's only one leg, which is a big one leg right there, and that may be the confusion. But otherwise, if your question is more towards semantic segmentations, many of these models actually do a very good job. Some of the last models I showed you, for example this, you look at how well this model is performing compared to so many other models available, even PointNet, PointNet++, multi-view CNN, PointCNN, DigiCNN, or KD network, all of these models I think are not that great compared to the PVNet using based on AlexNet model. So every time there's a new model that comes out there, it's better than the state of the art. But right now I think the main focus of point cloud processing is semantic segmentation, because in all the 3D modeling, they want to identify where the chair is so that they can take the chair out and put something else there, and then you can do the visualization. Many point cloud solution processing is also used in augmented reality too. Have you used the IKEA app on your iPhone? Let's say you find an interesting chair, you pick the image and go to your kitchen and then show it to the kitchen and then drag and drop it. It'll tell you exactly how the chair looks in your kitchen, because it's doing an AR or a VR of your room. And that type of apps I think are becoming more and more, both gaming and also for consumer consumption. In both situations, I think point cloud processing is really interesting.
But I was thinking, maybe it's a non-problem, but how can I know I have the single points, how can I know which one are connected in the object that I have scanned?
That's the intelligence of the model. Model will figure out which are the points which belong to this chair and this chair. And sometimes if there is an empty space here, of course there will not be any points. Imagine when you're taking a 3D point cloud and I'm actually standing here, so you see these two chairs, and even though I'm here as a depth perception, if you don't feel the depth, if you see from here, it looks like my t-shirt is right next to each other, and then the point clouds may get confused. But a 3D point clouds is 3D, so you actually get the depth information too. And the models are intelligent enough to figure out which are the cells that belong to points that belong to each of the object. But that's a whole objective of developing all these models. If you want to semantically segment, it'll actually find out where it ends. The problem many of the models is having is when the objects are so close to each other, it's called occlusion or even self-occlusion. If there are blocking itself, some other portion. If you look from this side of the chair, this leg you can't even see. So the chair itself is blocking its leg, and then the model cannot figure out. Some of those fine, I remember in PointNet model when they were presenting, if you have a chair with a back support and if you have multiple rods, like some of the chairs have rod supports, the model was having difficulty in finding out what the rods are and what they are doing there. And sometimes it just says that's an empty space, or sometimes it says it's the entire chair is the entire back support is a chair, and then it's not doing a good job. So those minor local features models are not picking up, especially if you have the point clouds becoming more and more high definition and you have more points in a cloud, and then you have a model which needs to process it really fast to get a sub-second response rate, let's say 20 or 50 millisecond response rate. The model has to, you have really high computing power to understand the point cloud. Half a terabyte, which means almost 200 million points in an image, and the model has to understand each of the point, which object it belongs to. It's a difficult process. So right now, it's all happening in the cloud. I don't think it can come down to mobile devices, but there are some AR and VR solutions available on a mobile device. For example, if you hold an iPad app, you can actually see, like even on your cell phone, the IKEA app, you can do it. But then I think the accuracy rates are low, but then they're doing really simpler. You have a question, sir?
I would ask about the performance. Those that are set available, how many classes are managing? Because usually you model strength of more classes with less accuracy compared with the same model strength of less.
Yeah. See, more classes, less accuracy is a right statement. But if you have more classes, but you also have more data set, more data points, then the accuracy rate goes up too. So that, having said that, for example, this modern land actually has both 10 classes. You have a data set with only 10 classes, and you have another data set for modern land with 40 classes. And people have actually trained the models both modern land 10, modern land 40, and the accuracy is really, really high. Some of these data sets are indoor data sets where you actually have offices and chairs and tables and bedrooms and lamps and other thing, and you have data sets which are outdoor. Let's say you use for an autonomous car, let's say pedestrians and cars and the electric poles and trees. There are data sets available too, but they're not really large number of data sets available. For example, we are looking for a data set of a factory, multiple types of factories and pipes and pumps and walls and turbines. We're not finding data sets which actually are annotated. So we do know that if I do an annotation of, we have for example 10,000 images, point cloud images, and each point cloud will take, I don't know, 5 to 6 hours. And even if it's a cheap location, let's say I send it to some cheaper country, $10 per hour, which is almost, let's say, $100 per image. And if you're talking about 10,000 images, you got to really have funds from the government or some research organization. You can't have companies afford to spend that much money and time for annotation, because it takes 5 to 6 hours per image, and you're talking about 10,000 images. So you can't hire 10,000 people, because training them is going to be a difficult process. So that's the reason why the research is slowing down. It's not the techniques of 3D point cloud processing using neural networks, it's the availability of data sets. That's a big problem. So I think your question is valid in terms of if we have how much data sets we have, or these are the limited data sets, but even these, I think there are good number of data sets. These are all open source data sets. But companies like Google, for example, or Baidu, they have been collecting their own 3D point cloud data sets and annotating themselves and using it for their own autonomous car solutions. I don't think they have open source data. I don't know, I may be wrong too, but I haven't heard of companies like that open sourcing the data sets.
About the data set, there was only one paper in the past comparing the performance of CNN to be trained on synthetic pictures or real pictures, showing that the performance was lower when trained on synthetic data.
Yeah.
Here in 3D points appear, I don't know, question is, are synthetic
initial approach, even for 2D processing, where can we mix some real data, real images with synthetic data images and combine it and train a model? What people have found is if you are testing the model on real images, the training also has to be on real images. Otherwise, it gets really confusing for the model. Because synthetic images, they look very, very fine surfaces. They have unnatural edges, unnatural curves, unnatural surface textures compared to a real image like a cat or a dog or a human being versus synthetic cat or a dog or a human being. There are a couple of approaches I've seen where if you don't have the data, can you do synthetic data creation, do a transfer learning, and then use the model for testing. I personally don't believe that would be a very effective method in terms of accuracies. The same logic applies for 3D processing too. If you have the model being used for inferring on real data sets, for example, if a room like this, and if you want the model to figure out where the wall is and the roof is and where the chairs are is, you should train the model on such real life images and not synthetic images, because it really gets confusing for the model. But I have not seen enough research which has proven the other way around. When you read these papers being published, do remember people publish papers only on the ideas they were successful. They don't publish on a failed idea. So we don't know what all things don't work. We only know what works. And hence, let's say if you publish a paper, for me to build on something, I need to also know what ideas failed for you, so that I don't repeat the same ideas. But that we don't know yet, because it's very expensive to do and people just don't have time to reveal. And hence today, if you look into all the conferences and papers published, you get appreciation only for being successful. You don't get appreciation for failing number of times, because you want to even share your failed experiments too. You don't get to see that. So I don't know whether that really works or not. I do know a couple of papers, they've tried it, but the accuracy rates dropped a little bit. But would it be an absolutely good idea to do a 3D point cloud with synthetic and real data sets together? I don't know. And I don't think my company would be interested even in doing that experiment too. So we want someone else to do the experiment, and we want to find out if someone has done the experiment and failed, then I would like to know, but no one knows that. So I don't know the answer, we just can't. We just have to wait for some more time. Maybe some new techniques will come. Maybe I think, remember capsule network was introduced in 2017. Till then, regular CNN models, let's say you have a human face. Human face, it classifies as a human face because there are 2 eyes, 1 nose, lips, and 2 ears. But CNNs, the regular CNNs, if I have 1 eye here, 1 ear here, my mouth here, and then the other ear here, the model still thinks that's a human being. But it's not a human being, right? It's something random thing. Capsule networks actually came out to identify the hierarchical structure of various components in an object. That solved a little bit of the hierarchy, lack of hierarchy in CNNs. There are so many such experiments, such techniques need to come in the near future to go back and answer that question about synthetic data versus real data, how much of that you can mix, and what will be the differentiation and stuff. So the answer is
I have a question about a specific problem which is not object recognition. For example, I need to go to a garage, make a 3D scan of a car, and then I have to create the mesh. At the moment, we use the points as reference for mesh creation. But I didn't find any kind of software that is able to automatically create the mesh. For example, MeshLab or other software. Do you have some idea about this kind of problems, which is not object recognition, but it's a creation of a mesh from?
Sure. I don't have an answer, and since I don't know,
Okay.
but then I would actually go back and question your question. Why would you want meshes to be created when you have models available which can take the raw point clouds as is without creating meshes.
Because I need the mesh for my
Okay.
process.
Okay, then I don't know, I'm not an expert on that.
Okay, okay.
My focus is on creating AI models. They can do semantic segmentations or object
Okay.
detection. And I know as of today, based on the research, I can just use the raw point clouds without going for meshes. Meshes was done a year ago, 2 years ago, because at that time people thought the unorganized, irregular data of a point cloud need to be converted into a regular and organized data set, and then I can use my 2D image processing techniques on this data because now it's an organized data. But that is no more required because some of the models can directly take the raw, unorganized point cloud data.
Okay.
I was thinking about training a model like this, and a question comes into my mind about cross-validation. You know, thinking about a model when we have a data set that 3D images, I can imagine how to split them so we can perform cross-validation. I'm thinking about this kind of models and images to 3D images. I cannot imagine how this can be done. So, can you explain us?
Yeah. Cross validation, I don't think you actually do in this type of examples. Let's say you're doing a supervised learning for the model, a supervised training. You have a point cloud annotated, and then you use techniques like RCNN, fast RCNN, or a faster RCNN, or a mask RCNN. In other words, you actually can draw the boundaries of the images, and you want the model to start predicting where the boundaries are, and every time it makes a judgment, you will tell, no, that's not the right boundary, here is the right boundary, and then you keep on doing it multiple times, and if you, let's say, if you do a 500 or 1,000 epochs of the whole data set, model starts understanding. I don't think you have to do a cross-validation. I have not seen a scenario where I would do a cross-validation, but I'm actually doing a pure supervised learning where I'm just doing, I'm defining a nice loss statement and then run the feed-forward model and then do a backpropagation and then let the model learn. So I don't think if I understood your question, but if I understood your question right, but I don't think you do a cross-validation in this part. Cross-validation happens when, let's say, typical machine learning solutions of, let's say, predictive analytics, and you have a bunch of data, and you want to segment the data, and then, let's say, you make the data set into 5 different pieces. One piece is for cross-validation, one piece for testing, and then you train the model on the other 3 pieces, and then you mix it back again and create 5 new pieces and then do the same thing, so the model can understand continuously. But I don't think that in image processing you need to do that. Yeah. Okay? You have a question? Last question.
I know that a lot of people are working on convolution on graphs, and a 3D point cloud could be interpreted as a graph. What do you think about these type of models? Are there any connection with the models that you show?
Yeah, so I mentioned earlier, the very first slide, there are graphs, so 3D representations can be in graphs and also in meshes too. And in both the situation, in the graphs and meshes, the objective was to convert the irregular data into some sort of regular data, so that you have a structure, you can measure one point from the other point and keep on going to the other points. But once the PointNet model, which I talked about, came out, where they said you can use point clouds data as is without making any changes, without making into a multi-view or without making into volumetric data. For example, a couple of papers were published in 2016 creating voxels. Let's say you have an object of a rabbit, right? It shows there, but you assume that rabbit is full of all the material in it, and then you voxelize it. All of these models showed, even including this 2.5 dimension RGB data too. All of these models did a good job initially, but right now the science has come to that level where you don't need to do any of these pre-processing of the data. You can just use the raw point clouds, give it to the model, and the model can figure out. So in that context, any of these pre-processing, for example, you don't need a multi-view view of an object. Like for example, if you have a point cloud image of it, you can take a 2D snapshot in this view, turn the point cloud, take a 2D snapshot of the same chair from a different perspective, and take multiple such views and give each view stacked on top of each other to the model to make a classification. Even that is not required anymore, because model can take the entire point cloud in as is without having to make changes. So meshes, graphs, RGB data, multi-view concepts are all kind of older technology. It's no more the latest technology. I would rather want to use a model which takes point clouds as is. And there is science available for that. So I would rather just go with that. Okay, thank you very much. Really appreciate it.
Thank you so much.
Yeah, thank you. Thank you very much.